Hello, my dear, and welcome to our astronomy course. Okay, today we are going to continue in study star. And you have learned how to find the luminosities, diameters, and masses of stars. And now you can put those data together to paint a family portrait of the stars. Okay? As in any family portrait, both similarities and differences are important clues to the history of the family. As you've been trying to understand how stars are born and how they die, ask a simple question. What is the average star like? Answering that question is both challenging and illuminating. If you want to know what the average person thinks about a certain subject, you take a survey, right? If you want to know what the average star is, like, you must survey the stars. Such surveys reveal important relationships among the family of stars. Not many decades ago, surveying large numbers of stars was an exhausting task. But modern computers have challenged that. Specially designed telescopes controlled by computers have changed that and can make millions of observations per night. And high-speed computers today can make millions of observations and analyze these vast surveys and create easy-to-use databases. Those surveys produce mountains of data that astronomers can mine while searching for relationships within the family of stars. What could you learn about stars from a survey of the stars near the sun? Because the sun is believed to be a typical place in the universe. Such surveys could reveal general characteristics of the star and might reveal unexpected processes in the formation and evolution of stars. Study the family of stars and notice three important points. First, taking a survey is difficult because you must be sure you get an honest sample. If you don't survey enough stars, or if you don't notice some kinds of stars, you can get biased results. Are you agree with me? Second, most stars are faint and luminous stars are rare. The most common kinds of stars are the lower main sequence red dwarf and the white dwarf. A survey revealed that what you see in the sky is deceptive. The vast majority of stars, including those near the sun, are quite faint but luminous stars. Although they are rare, are easily visible even at great distance. Many of the brightest stars in the sky are highly luminous stars that you see even though they lie far away. The night sky is a beautiful carpet of stars, but they are not all the same. Some are giants and even supergiants, and some are dwarfs. The family of the star is rich in its diversity. If you survey enough stars and plot the data in an HR diagram, you can see the patterns that hint at how stars are born, how they age, and how they die. If you label an HR diagram with the masses of the plotted stars, as in this figure, you will discover that the main sequence stars are ordered by mass. The most massive main sequence stars are the hot stars. As you run your eye down the main sequence, you will find successively lower mass stars until you reach the lowest mass, coolest, faintest main sequence star. Okay? Stars that do not lie on the main sequence are not in order according to the mass. Giant stars are jumble of different masses. And supergiant, although they tend to be more massive than giants, are in no particular order in the HR diagram on their main sequence. In contrast, the white dwarf have about the same mass, somewhere in the narrow range of half to about 1 solar mass. As shown by the systematic ordering of mass along the main sequence stars follow a mass-luminosity relation. The more massive a star is, the more luminous it is. So you may see in this. Let's look at this. Okay. In fact, the mass-luminosity relation can be expressed as a simple formula with this reasoning with numbers. Giants and supergiants do not follow the mass-luminosity relation very close, and white dwarfs do not at all. In the next 2 modules, the mass-luminosity relation will help you understand how stars are born, live, and die. The density of stars reveals another pattern in the HR diagram. The average density of a star is its mass divided by its volume. Stars are not uniform in density, but are most dense at their centers and least dense near their surface. The center of the sun, for instance, is about 150 times as dense as water. Its density near the visible surface is about 3,400 times less dense than Earth's atmosphere at sea level. A star's average density is intermediate between its central and surface density. The sun's average density is approximately 1 gram per cubic centimeter. It's about the density of water. Main sequence stars have average densities similar to that of the sun, but giant stars, being large, have low density average, but low the average density, ranging from 0.1 to 0.01 gram per cubic centimeter. The enormous supergiants have still lower densities ranging from 0.001 to 0.501 gram per cubic centimeter. These densities are thinner than the air you breathe. And if you could insulate yourself from the heat, you could fly an airplane through these stars. Only near the center would you be in any danger, for there the material is very dense, roughly 3 million times the density of water. The white dwarfs have masses about equal to that of the Sun, but are very small, only about the size of our planet Earth. That means the matter is compressed to enormous density. On Earth, a teaspoonful of this material would weigh about 15 tons. Imagine this fantastic value. Density divides stars into three main groups. Most stars are main sequence stars with densities like that of the Sun. Giant and supergiant are very low density stars, and white dwarfs are high density stars. You will see in later modules that these densities reflect different stages in the evolution of stars. Let's see this scientific article. What kind of stars do you see if you look at a few of the brightest stars in the sky? This argument shows how careful you must be to interpret sample observation. When you look at the night sky, the brightest stars are mostly giants and supergiants. Most of the bright stars in Canis Major, look in this symbol of this flag, for instance, are supergiants. Sirius, one of our favorite stars, is the brightest star in the sky, but it is just a main sequence star. It looks bright because it is nearby, not because it is very luminous. Okay? In general, the supergiants and giants are so luminous that they stand out and look bright, even though they are not nearby. When you look at a bright star in the sky, you are probably looking at a highly luminous star, a supergiant or a giant. Now revise your argument. What kind of star do you see if you look at a few of the stars nearest the Sun? Try to do it. And now let's go. Distance is critical in astronomy. Your goal in this lecture was to characterize the stars by finding their luminosities, diameters, and masses. Before you could begin, you needed to find their distances. Only by first knowing the distance to a star could you find its other properties. Astronomers can measure the distance to the nearer stars by observing their stellar parallax. The most distant stars are so far away that their parallaxes are unmeasurable small. Space telescopes about Earth's atmosphere have measured the parallaxes of huge number of stars. Stellar distances are commonly expressed in parsecs. 1 parsec is 206.265 astronomical units. The distance to an imaginary star whose parallax is 1 arc second. 1 parsec equals 3.26 light years. The amount of light received from a star, the light flux, is related to its distance by the inverse square law. Okay? Once you know the distance to a star, you can find its intrinsic brightness expressed as its absolute visual magnitude. The apparent magnitude the star would have if it were at 10 parsec away. The luminosity, usually measured in a Latin letter L capital of a star, found from its absolute magnitude, is a measure of the total energy radiated by the star in 1 second. Luminosity is often expressed in terms of the luminosity of the sun. The strength of spectral line depends on the temperature of the star. For example, in cool stars, the Palmer lines are weak because atoms are not excited out of the ground state. In hot stars, the Palmer lines are weak because atoms are excited to higher orbits or ionize. Only at medium temperature are the Palmer lines strong. A star spectral class or type is determined by the absorption line in its spectrum. The resulting spectral sequence, usually we have a letter O, B, A, F, G, K, and M, is important because it is a temperature sequence. Look in the opposite side. But classifying a star, the astronomer learned the temperature of the star surface only. Long after the spectral sequence was created, astronomers found the L dwarf and T dwarf as temperatures even cooler than M star. A spectrum can tell you the chemical composition of the star. The presence of spectral line of a certain element shows that the element must be present in the star. But you must proceed with care. Lines of a certain element may be weak or absent if the star is too hot or too cool. The Hertzsprung-Larsen or HR diagram is a plot of luminosity versus surface temperature. It is an important graph in astronomy because it sorts the stars into the categories of size. And roughly 90% of normal stars, including our sun, form the main sequence with this main sequence on the diagram from left upper corner into right down corner. With the more massive stars being hotter and more luminous. The giants and supergiants, however, are much larger and lie above the main sequence. Red dwarfs lie at the bottom end of the main sequence. Some of the white dwarfs are hot stars. Red dwarf, sorry, and white dwarf. And white dwarf are very hot stars, but they below the main sequence because they are so small. The large size of the giants and supergiants means their atmosphere has the low densities and their spectra have sharper spectral lines than the spectra of main sequence stars. In fact, it is possible to assign stars to luminosity classes by the width of their spectral line. Class 5, if this is diagonal or the down, are the main sequence stars. Giant stars, class 3, have sharper lines, and supergiants, class 1, have extremely sharp spectral lines. Astronomers can use the locations of the luminosity classes in the HR diagram to estimate the distances to stars in a technique called spectroscopic parallel. The only direct way you can find the mass of a star is by studying binary stars. When two stars orbit a common center of the mass, astronomers find their masses by observing the period and sizes of their orbit. In a visual binary system, both stars are visible and the orbit can be mapped. But in a spectroscopic binary system, are so close together they look like a single point of light, and the orbit can't be observed entirely. In an ecliptic binary system, the orbits are edge-on, and the stars cross in front of each other. The resulting brightness changes in the light curve and can reveal the diameters of the stars as well as their masses. This way, in the neighborhood of the sun, shows that lower main sequence stars are the most common, and so they are faint and hard to find. The mass luminosity relation says that the more massive a star is, the more luminosity it is. And main sequence stars follow this rule closely, the most massive being the upper main sequence star, and the least massive, the lower main sequence star. Giant and supergiant do not follow the relation precisely, and white dwarfs are not at all. Given the mass and diameter of a star, you can find its average density. On the main sequence, the stars are about as dense as the sun on the upper part. Yes, you can see here. But the giants and supergiants are very low density stars. Some are much thinner than air. The white dwarfs lying below the main sequence are tremendously dense. I think it's more than enough for today. Okay? Any questions or propositions? No? I hope you enjoyed this lecture, and I'm looking forward to seeing you next time. Bye.